In section 7.4, we get to the very extremely important topic of Lagrange multipliers. And it helps us find the maximum or the minimum value of some function subject to a certain constraint. So we have a function, a two-variable function, f of x comma y, and the function happens to be, you multiply x times y. So f of 2 comma 3 would be 2 times 3 equals 6 or whatever. But we're not just looking for the maximum of this function. This is subject to a certain constraint. So for some reason we have a constraint that 3x plus y has to add up to 720. So I want the numbers 3x plus y that add up to 720, and I want there are infinite combinations of numbers that could do this, but I want the one where x times y is a maximum. So that's what I'm trying to do here. And here we go. First, we have to look at we have to create a function capital F of x comma y comma lambda. Now there was no lambda here. We just invented a lambda. And that's going to be equal to f of x comma y, which we had up here, plus lambda times g of x comma y. Now g, what is g of x comma y? G is based on the particular constraint. So in our problem, the constraint was 3x plus y equals 720. I basically just take the 3x plus y part, subtract the 720, and that's my g. So if my constraint says 3x plus y has to equal 720, my g function is going to be 3x plus y minus 720. And we're ultimately going to set this equal to 0, because if I bring 720 to the other side, I have a 0. If my constraint is x plus y equals 47, then g of x comma y would be x plus y minus 47. I'm just giving you examples of how to find the g. If my constraint was that negative 2x plus 11y equals 414, then g of x is going to be negative 2 plus 11y minus 4. I hope you're getting the point of this. If my constraint is that x squared plus y cubed that's equals 17, then g of xy is going to be x squared plus y cubed minus 17. That's how you make g. You basically take the constraint and bring everything over to one side. Bring the constant over to one side. So that means that in our product, f of x comma y is xy, which it says right up here. Lambda is just this number I invented, which we're going to solve for, but we get to that. And lambda times g, so g is 3x plus y minus 720. I took the constraint, 3x plus y equals 720, and I just to bring the 720 over to the other side. So there we go. And now let's just get rid of the parentheses. So capital F. Notice I started with a small f, and now that I have a capital F. So we always use that notation. We start with a small f and we create this capital F. And we're using all this. So we're creating a lambda, creating a capital F, but we're doing it to find the maximum value of small f. Anyway, I get xy plus 3 lambda x plus lambda y minus 720 lambda. Now the next step is that I need to calculate fx, fy, and f lambda, meaning the partial derivative of capital F with respect to x, the partial derivative with respect to y, and then the partial derivative with respect to lambda. I'm gonna calculate each one, which is not that hard to do, and then we're going to set them all equal to 0. So fx is y plus 3 lambda, because I treat the y is treated like a constant, so the derivative of a constant times x is just a constant, and here the 3 lambda is a constant, and there we go. And these guys here don't have any x's in them, so they're just constants. They all disappear. Fy is, well, x is a constant, so I bring down the constant. That doesn't have any y in it, so it just disappears. This is a constant times y, so I bring down the constant. And for f, now f lambda always just winds up being g, if you notice. And you can see that because there's no lambda here. There's a lambda here, and there's no lambda inside the g, so the g is just a constant. And, it's not a coincidence that f lambda always just winds up being g. Because if we would figure it out, we'd get, from here we'd see 3x, from here we'd see plus y, from here we'd see minus 720. So we could figure it out and get that, or we could just say, hey, it's just going to be g. Either way, what we're going to do now is we're going to use the top two equations to solve for lambda by solving for y in terms of lambda, solving for x in terms of lambda, and then substituting those into the third equation. So let's do it. From the first equation, I see that y is equal to negative 3 lambda. I just bring this lambda over to the other side. So I've solved for y in terms of lambda. From the second equation, I see that x is equal to negative lambda. How? I just brought the lambda over to the other side. Don't forget, these guys equal 0. Now I'm going to take my y, which is negative 3 lambda, plug it in here. Take my x, which is negative lambda, plug it in there. And that's going to give me negative 3 lambda minus 3 lambda. Now, because it's 3 times negative lambda, which is negative 3 lambda. And then it's y, which is just minus 3 lambda. And then minus 720 equals 0. Now I just got to solve for lambda like I would any simple algebra equation. And you get 6 lambda equals 720. Negative 6 lambda equals 720. Lambda equals negative 120. That's just a simple algebra to do that. And I'm almost done, because all I have to do now is take my lambda and use that to construct the x and the y, because these are the x and y's that are going to work to maximize. So I get that y is equal to negative 3 lambda, which comes out to positive 360. X is equal to negative lambda, which comes out to positive 120. And my function, f of x comma y, the maximum is going to be, so these points are going to be the magic points that are going to make my maximum. That's what Lagrange Multipliers does, as we explained. My maximum is going to be f of 120 comma 360, because that's the x and the y that I have. And that's just the product, x times y, which is 120 times 360, which is 43,200. And that is how we do that.